So hi everyone. In this clip, I want to review a couple of properties of classical light waves. This is essentially the contents of my QO Notes chapter 1a. And this settles a bit of notation, and now we can have a look at what are actually the quantities that we're going to quantize. All right, then. So let's write down the electric field of just a plain traveling wave. It has this form where you have an amplitude, polarization vector, a phase, it propagates in the k direction, and it has a frequency omega. Now, important to realize that this thing must be real, simply because the electric field can in principle be measured, so it has to be real valued. So the amplitude must be real, but also the polarization vector must be real valued. Now, it is usually convenient to write this as the real part of something complex. So now we write this as the real part of this exponential here. And now we can relax the condition that E0 and E are real. So these can now be complex. And in fact, we can now absorb the phase into the amplitude. So this can now be amplitude times e to the I phi, where phi is, of course, this one up here. And if we just take this exponential and add the complex conjugate, then we have something real again. And the convention is now that we say that this term we call E plus, we call that the positive frequency component. Positive frequency component, which varies like e to the minus I omega t. Okay, so that's something you should just remember. Positive frequency is what we call e to the minus I omega t. And of course, this is the negative frequency component, which then has a plus I omega t. Sort of as a sneak preview towards field quantization, we're going to see that E plus, the positive frequency component, will be associated with photon annihilation. Okay, and the other one, the E minus, is going to be a dagger, which is going to be the creation of a photon. Now, furthermore, the electric field, of course, must be transverse because the curl of E must vanish. So the polarization must be perpendicular to the k vector with propagation direction. And if the wave propagates along z, then this polarization must therefore have this form with this component 0. And so we can think of this as a two-component complex vector, which we might call a spinor. And that's handy because this will be a template or a model system for other spinors that we will encounter, such as the state of a two-level atom, or the two light fields going into a beam splitter, and some other ideas. So if the polarization, it could in fact be real, and like if Ex and Ey are in phase, then you could write it as a real vector. In this case, it will be linear polarization. But of course, if X and Y are 90 degrees out of phase, you get circular polarization. And then you write 1I or 1 minus I. Another thing we need to look at is the Poynting vector, because we are now interested in what we would measure in the lab. So if you have a photodetector, it measures energy or intensity, photons per second, so things like that, but not field amplitude. It measures energy or intensity. Now the Poynting vector gives access to that. So the Poynting vector is a quantity that has the units of watts per square meter. So it's the power flowing through a unit area. Flowing through a unit area. But this thing also is has a direction. It is a vector. So it also tells you what direction the energy is flowing into. But to calculate it, we need the magnetic field. So Maxwell's equations tell us how B is related to E. So we have to, if you take the time derivative of B is the curl of E. And now we make use of the fact that, that we have traveling plane waves, which means that the time derivative can be replaced by minus I omega, whereas the spatial derivative can be replaced by just I times the k vector. And this is simply a consequence of the exponential form of the traveling waves. And then the Poynting vector is going to be E cross B, which is proportional to E cross K cross E. Then you use one of these vector identities, which tells you that this is the same as E dot E times K minus E dot K times E, like so. And of course, this one vanishes because the field must be transverse. And so then you see that the Poynting vector is essentially E squared. It's the square of the amplitude. Now, furthermore, if you look at E squared, but what we will actually use for E squared is E plus times E minus. So we're going to write this is equal to E plus E minus. Then there's another term E minus times E plus, which is the same. So you can just write a 2 in front. And then there's other terms that go lost on the photodetector. They are not registered. And these are terms of the form like E plus dot E plus and also E minus, because this thing now goes in time like E to the minus 2I omega t, which is incredibly fast, because if we're talking about optics, then this omega is going to be 10 to the 15 or so hertz. Okay, so we're talking hundreds to thousands of terahertz, and photodetectors cannot detect such a fast signal, so it basically averages out, and all you measure is the slow component, which is the, let's say, the DC component, which is E plus E minus, which is therefore the proportion to the modulus of the amplitude squared. So this is then the intensity. It's E modulus of the amplitude squared times epsilon naught C. So what you should remember from this is that the positive frequency component, E plus, varies like E to the minus I omega t. And we shall see later that this is associated with the photon annihilation operator. Okay? And the photodetection signal is the square of the amplitude modulus, which is then proportional to energy, power, number of photons, etc. So, one question about this video. We replaced the time derivative and spatial derivative by omega and k to get the Poynting vector, which works fine if we have a traveling plane wave. But now let's consider a standing wave, like in chapter 2.1 of Geary and Knight. Can you give the corresponding expression for the Poynting vector? So what is the Poynting vector of a standing wave? And then when you found it, please interpret the result. So ask yourself, does it make sense? Is this what I would expect for the Poynting vector of a standing wave?